Oh my God. This one opens real slow. Okay. So we're going to start on chemical structure and reactivity. Hopefully this one will go a bit faster. Okay, so you're going to notice that this actually is going to kind of pick up from the previous orbital materials. And so here we see a very stereotypical coordination. Okay. Notice that's a little bit different than a normal reaction, isn't it? Okay. And so why am I mentioning coordination when we're talking about chemical structures and activities? What's one of the things that's going to show up in this one? Acid bases, right? Acid bases. The stereotypical coordination reaction, right? Good or bad? No? Really? Huh. So coordination, what we're going to have is we'll have two atoms, right? They have their atomic orbitals. And so we'll have the HOMO and the LUMO. In these cases, I'm sorry, these are molecules in these cases. Doesn't really matter, but so we'll have like a H plus or a hydronium, right? And then we'll have the base, which has extra electrons, right? So you got your lone pair, you have your acid over here that's deficient. Okay? And so what they're going to do then is they're going to react, and they're going to form a new set of orbitals, right? And those new orbitals, one's going to be lower, one's going to be higher. Now, because only one of them is bringing electrons into this, it automatically just goes to the lower energy orbital, doesn't it? And this is stereotypically why coordinations occur. Okay? And they can all kind of be written out like this. Yeah, they have other molecular orbitals that would have been involved with the overall structure, but the reaction itself, that's all that really matters. Okay? Because the other orbitals are going to be there no matter what, right? Okay, so let's look at some historical definitions of acids and bases. You guys may remember the Arrhenius Ostwald one. Probably just Arrhenius acids and bases is what you heard. Yeah? Okay, so that one is, what's an acid? Increases H plus in solution, right? What's a base? Decreases H plus in solution, right? Or you may have heard it as increases OH minus in solution. Very water-based definition, okay? This definition really only works like that because it's in water, right? And so if you wanted to be more specific, it would be dissociation of H plus and dissociates OH minus for the base. This would be something like this, where we have H plus reacts with OH minus, would give us water. For example, here we have a dissociation that produces H plus. Keep in mind, though, it's never actually H plus in solution. Okay? That's just not possible. So remember that this one always depends on an equilibrium, which is water, right? Everything's water-based with that. The next one would be the solvent system. So whatever increases the cation form of the solvent is going to be your acid. This works if you think about it, like H3O plus hydronium in water, right? Whatever makes that more, that's your acid, isn't it? Okay. And whatever increases the anion form on your solvent is going to be a base. And so in water, that'd be OH minus, right? Your anion form. Very similar definition, but it can work in other stuff than water. Okay. The Bronsted-Lowry, this is probably the one you guys remember the best. This is the proton donor, proton acceptor. So whoever donates a proton is an acid, whatever accepts a proton is a base. Organic chemistry will sound real familiar with this one. Lewis acid and base. So electron pair acceptor is an acid, Lewis acid. Electron pair donor is a Lewis base. It's like 50 to 70% of all reactions in organic chemistry, right? Right there. Lewis acid base, there you go. FMO theory is going to be reacts using its LUMO, reacts with using its HOMO. So the base is going to react using its HOMO, highest occupied molecular orbital, because it has extra electrons, right? The Acid, on the other hand, is going to react with its LUMO, and that's actually what we just saw right there. So the Usanovic is going to be the accepts negative species is going to be your acid. Donates positive species is going to be the base. Okay, so let's see some more work on this. So you may recognize this. What's the typical measurement we measure acids in? pH, yeah. And pH, again, is a water-based measurement, isn't it? Keep in mind that's never actually H+, is it? It's always H3O plus in water, right? But I'm going to say H+. Are we all okay? Okay. And so this right here is the auto ionization of water. And remember that whenever you have a form that has an acid and base form, you're always going to get some degree of auto ionization. This actually is what gives you the pH range of 14 in water, right? Because it can it auto ionizes in water at room temperature. That's going to be this for its equilibrium constant, room temperature being 298 Kelvin. And that is 10 to the negative 14. If we were to plug this in and get the negative log of the H+, we would have a pH of 7, wouldn't we? If we did it for the OH, we'd have a pOH of 7. And so that's actually what makes neutral pH 7 in water at room temperature. If it's not room temperature, you would actually have a different, slightly modified pH. That would be neutrality. If you had some other substance than a water, for example, ammonia, you would have a different K, wouldn't you? See that? So this would be the autoionization of ammonia if you used ammonia as your solvent. And so right here, that would be a 27 pH scale, right? So it'd be a 0 to 27 sort of thing, okay? And so on. If you were to use sulfate, for example, you'd have this as your set of ions, and that would be the solvent. That would be then the acid and base forms for sulfuric acid. And then that would be your scale right there. Okay. Okay, so let's go ahead and look at these. These would be your effective pH range if it were water as comparison. So the water system is 0 to 14, just like you probably already knew. And that was the pH range you're probably used to. If we start looking at different substances, for example, we took HF, we would have an effective negative 20-something pH be an acid. And anything above, what is that? Something like 5, 4, negative 4 would, these are all bases up here in HF. Okay. And we can go the other way with something like DMSO. And so you may have noticed that whenever we were doing organic chemistry, we were like, this is acidic and it has a pH of 20. That pKa was like negative 10 to the negative 20, right? And in a normal situation where you're in water, that would not have been an acid, right? In organic chemistry, it's an acid. And that's because we're in solvents like this, right? We're in DMSO, and so you can have an effective pH of 20-somethings, and you could still have some degree of acidity with something that's higher, right? And this is due to the solvent leveling effects. So the solvent is the one you're always reacting with. In any acid-base situation, the first thing you react with is the solvent. Okay? And so, for example, if we add any acid into water, what do we actually react with? Do we ever react with HCl? No. We react with H3O+, don't we? We add HBr, we react with H3O+, don't we? It always dissociates, creates our acid, which is H3O+. Yeah. Bases, same thing. We are really reacting with OH-, right? It's going to be very unusual for the actual base itself to stay together and actually get to the other reactant. Okay. So this right here is some examples of some different situations. So here we have CO2 reacting with water. This creates H2CO3. This is actually going to be an acid, and this is the acid in your blood, actually. So this is then going to dissociate to H plus and HCO3 minus. That's actually the buffer system in your blood, isn't it? Okay. Over here, we actually have irons. Notice they're going to make a hydrated shell around the iron. This will actually stabilize those irons if they want to lose H pluses. Okay. And so that would be your complex ion right there. And then they lose H pluses. It goes down in charge. See that? Okay. And so iron can actually be an acid in water, of course. Does anybody have any questions about those so far? Okay. So the molecular orbital interaction between a metal, which is a Lewis acid, and a ligand, which is a Lewis base, this is going to form what's called a coordinate covalent bond. So here we have, for example, our last example here, which is copper 2 plus. We have ammonia here. That has a lone pair, right? And so those lone pairs are going to create coordinate covalent bonds to the copper, like so. And those are then going to stabilize that complex ion right there. Okay. Everybody understand why it's being called a complex ion? So it's an ion that then has ligands. So it's a metal ligand ion. Okay. And it has a charge, so it can actually float around in water as an aqueous as that complex ion, right? So for example, if you were to crystallize this out, you would need another anion to do that with. And there's another anion probably floating around this. Okay? Yeah. Yep. Yeah, you'd have two chlorine atoms in solution or something, right? Whatever anion. Yeah. But this is actually in actual real world aqueous systems. This happens quite a bit. Okay, because in real world aqueous systems, you have things with multiple charge, right? Not just +1, +2, alkali earth metal sort of stuff. You have coppers and irons. So those create complex ions quite often. So right here, we actually see the formation of that. And so we're going to get a metal. In this case, it's copper 2 plus. It's going to react with a ligand. Now notice the ligand doesn't have a charge, right? So it doesn't change the charge at all. Okay. It does bind to it, and some of that electron density goes into a bond, which is going to be that coordinate bond, right? And so we get the ammonia on there. This is then going to be copper with ammonia 2 plus. And it just makes that same coordinate covalent bond that we had looked at the beginning of the chapter, right? Okay, so these are some of the different types of compounds exhibiting Lewis acid behaviors, Lewis acid base behaviors, and I guess I'm stopping here. And I guess we'll just go ahead and stop here and we can pick up here next time. One thing I want to show you guys is these are the molecular orbitals, right, that you're making. So you have your atoms, they're combining into molecular orbitals. When you look at molecular orbitals, keep in mind that yes, they are your bonds. Okay, so for example, these the pi bond ones are the pi bond ones, the sigma ones are the sigma bonding ones, right? But that doesn't actually mean that it is this bond here that's that orbital. Okay? It's the sharing of electrons that would be involved in direct sharing, direct overlap of orbitals that are going to be these combination of sigma orbitals. Okay? So for example, if we start looking through these, we're actually going to see as we go up, we're going to get increasingly high energy, and that's because of nodes, right? And you can actually see the nodes. These are different arrangements of the nodes. Depending on symmetry, they're going to be higher or lower energy. Mm-hmm. Yes. It's the symmetric effect of them, right? So if they resonate with something else because they're same symmetry, that can cause mixing and lower the energy. or vice versa if they're the wrong symmetry, right? And so, like for example, we can see a kind of interesting lone pair here, and sort of a very similar to this, right? But instead, we actually have node right here around the middle one. Yeah. And so this would be a very similar interactions to these, right? Sigma. It's just a higher energy interaction. And notice these shapes, like this is not one of these bonds, is it? Those electrons exist in that whole area. Okay. And then you have the behavior where they're existing in opposite phases across it. Okay. And that's what those orbitals actually are. It's kind of an oversimplification when we go, these are your bond orbitals. Yes, they're the ones that are involved in bonding, but the exact shape of those orbitals is not going to be a simple bond when you have more than two atoms, right? When you have two atoms, it's pretty simple. But when you have more, it gets a little more complex. Did that make a little bit more sense? Okay. Yeah. Yeah. Now, these parts right here, to actually figure this out, these are calculations. You don't normally do these by hand. It would be incredibly difficult to do these by hand, even for something this simple. And so that's where you see this wave function Spartan Student Edition version 7. You can actually download that, by the way, for free. And you can generate those orbitals if you want for every problem. Takes a little while because you got to make them all and set it up and everything, but you could do that if you want. Yeah, we don't have a computational chemistry course. And I figured that most of you are not going to go into some sort of computational chemistry field. And it would be a very long thing to do. Like it would have eaten up our time. And we're already struggling, aren't we? I actually do have a. By the way, if you guys would be so good, who here still wants to do a tour of PACE? No? PACE Analytics. It's like a 11 building campus of analytical. They test all the sort of stuff from air samples for this company, environmental, this, EPA, and everything. Yeah. Okay. Okay. Would you guys be willing to tell me sort of, yeah. 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 He just went, do you mind if I tell?
Go ahead.
Yeah. Yeah. He applied for a lab tech job there and did a interview / tour, and really cool. Yeah. And it's a great place to get some like real world experience that they can then go on. They have like they do pay for people to go back, refund. It's kind of a cool thing. And they're always needing more people. So I'm gonna try to set up a tour. If you guys could give me an idea of what sort of time slots would work for you guys, I would appreciate it. Yeah, I kind of need to figure that out before I try to set up a tour, right? Yeah, we would want to do it. You all probably don't want to do it finals week, right? Week before? Okay. Okay. Yeah, kind of discuss together and find a time slot. I'll need probably a week or two to set it up. So give me. Uh-huh. Sounds good. Anything good on the paperwork? Anything interesting? Oh, yes. Okay.
You can just go through them like, yeah, they know.
Yeah.
And
How are we doing?
Okay.
Doing okay?
Yeah. How are you?
Fantastic.
Is that yours?
I am doing all right. That is mine. Thank you. Glad I need it for the rest of the day.
Apparently, I'm not going to be offering my mammalian next semester, so I got to fill out my people form to have general
Oh,
physiology.
okay.
I just filled it out. I just think
Yeah, I figured they probably have the same problems we do, where it's like limited faculty and limited.
name. Apparently, it's the same. It's just different. That means we have to fill out.
That's funny.
I mean, not a
Yeah.
big deal.
Yeah, it's not a big deal, but that is kind of amusing.
I thought I was in trouble. I've never been close to that before. Oh my god.
Uh-oh. Well, luckily it turned out. Okay. I didn't do too bad today. Oh, man, I need to do clean. Hey. What's you doing, please?
Pretty good.
Yeah, I like that. I really do hope you end up working,
Yeah. We'll see.
or you find something that pays amazingly well.
Either one.
I hope that's for you. But I just think that'd be a nice.
Yeah. Yeah. Especially after that tour. I mean, I was just like, I mean, I've only ever seen really this lab in like high school lab, but it was just like
Yeah, it's
mind
a whole
blowing.
different.
Yeah.
Yeah.
It was insane.
Yeah, honestly, this lab is not a good example of lab. I mean, keep in mind they didn't have any. They only had one organic solvent in the entire floor
Really.
before I came. Yeah, hexane. That's it. I'm joking.